Okay, so we will resume at the place where we stopped yesterday, and in particular at the point where we consider how to separate a model from its geometry, so the inner part of the model from the surface part of the model. So just to remind you, it is possible to take a set of rules. Here there is only one rule. You have a mixed between the geometry, which is represented by the F that the turtle knows how to interpret, and the A, which is, means nothing for the turtle. And the question is how we can separate this. So the idea would be to introduce a notion of abstraction, where the model rule and model L string would be only composed of nonsense modules. And in order to give geometric meaning to these modules, you would add new types of rules that are called interpretation rules, and that would be like these ones, where an S, which is the abstract version of the F, would be actually interpreted as an F later on, okay, in a second step, in a second process. And this makes it possible with the same model, either to produce this type of figure or this type of figure, just by changing the interpretation rule. Okay, so this is extremely convenient to separate the things and to not to mix up. Okay, so if we want to keep these rules separated, you need to use the first set of rules, which are called the production rules, in order to derive the different L string from the initial state of your model. Okay, so the P's here represent the rules that work on the model at the deep level, and then this makes it possible to compute at each step k a string that represents the state of the model at this step k, and then you use different set of rules, G, different from P, that are called interpretation rules, and that will read this L string here and transform it to a geometric interpretation. So you have two types of transformation: the horizontal one that go from one L string to the next L string of the model, and then you have at each step you may compute using other types of interpretation rule the geometric interpretation of the model. Okay? So actually it's a trick, but it's a very smart trick, because you use the same language to compute both things: the evolution of your system and how it should be represented using rules. Okay, and then you get a geometric string as opposed to the initial L string. That can be read by the turtle. So if we look at how it goes when you are in LPy, so at the beginning you have the axiom. The axiom is interpreted when you type rewind. The axiom is interpreted by the geometrical rules. If there are no geometrical rules, the turtle tries to read directly the axiom as it stands. And after you make the next step, then the turtle may read the next version of the L string and get the new geometric interpretation. So it's a bit computationally extensive, because you would compute each time the model evolution and its geometric interpretation, but it's a way to keep the things really well separated. Okay, so you see that the evolution, and what is important is that the evolution is really through, let's say, through time. It's not necessarily time, but it's could be assimilated to time. And this interpretation is independent of what occurred at the previous step or at the next step. Okay? This interpretation is really centered on the object that you computed at the step k. So in a way, it's a context-free interpretation of the string. Because if I look in the context of this full set of derivations, I'm not, to compute this, I am not looking at this. I'm not looking at what is after that, okay? And this also is extremely important because it will make interpretation extremely general because you don't need to go to look at the context in general. Well, there are cases where you need to have this type of thing, but it's a bit more complicated. So if you take an example, let's say that we have two rules, and you see that I use this S and this A that have initially no meaning for the turtle, just to mean that this is conceptual model. I start with the axiom A0, and then I have the derivation of the model, which is completely conceptual. The turtle cannot make anything about this. But this can mean that I have a segment of a plant with an apex, and this creates two segments with a new apex, with three segments with a new apex. So I can give a semantic interpretation, a botanical interpretation to this type of thing. So in my head, this means something about the plant. And now I want to say that this should also mean something for the turtle in order to interpret this. And then I define interpretation rules. So in this case, it's not important. I just took that at random. But the apex is a sphere, and the S should be interpreted a bit bizarrely with a cylinder with this type of formula to compute the length of the F. And then if I use this, you see that for each of the L string that is computed step after step, I can interpret using this rule. So for A0, I use this rule, and then I get this first geometric string. For S0, A1, I use these two rules, and I instantiate these two rules with this L string, and so on. Is that clear? Okay.
Maybe in the end, you would have examples of like exactly the same model, giving like two visually looking very different plants?
Exactly. You could have this. A plant, let's say it's a fish bone. Okay, you could give the fish bone completely different aspect, depending on whether you want to represent leaves by a certain model or a trunk with a curved shape. Or
this kind of validate the architectural model that you presented yesterday.
No.
Because
yes. Mm-hmm.
Because so the architectural models, so they are like really the production rules.
Ah, okay, I see.
And then so if you say like these two trees, they have really the same architectural model, and you say, but no, they don't look the same. And you say, but look, I just I have the same model.
Yeah.
I change the interpretation rules, and then I recapitulate the two trees. So it's a kind of validation that the claim of they have the two architectural model is plausible.
Yes, I wouldn't say validation because nobody said that this should be like nature. But actually, what we do in nature is that we do the opposite. We go the opposite way. Nature is presenting things that look on the surface different, and we try to abstract what is behind that is common to the different instance. And by doing this, we do the conceptualization phase. That it is exactly the opposite of this process. So I wouldn't say that this validates, but the two phenomena are dual of one another, and can be found in the human way of thinking.
So you wouldn't say that the separation between horizontal derivation and geometric interpretation has some biological equivalent?
It has some biological equivalent, but it's really a human perspective that you get this equivalent, this sort of similarity of functioning. It's really us that we are, as a human being, in my way of thinking, I make the distinction between this and this. Nobody says, and when we look at plants, we say, oh, but in this tree in the tropical forest, and when I look at this other tree, other species in the tropical forest, actually they grow the same way. But it's really a human interpretation of what is going on. Nothing was in nature coded so that they are similarly in a deep manner. It's really you that project your understanding on what is going on in the nature. So it's interesting for the discussion between us, so that because it's difficult to define all these things, but it's interesting so that we can think about this aspect. So I completely agree with your remark that it has something to do with the fact that different plants may create different architecture, whereas they actually derive from a common background model, architectural model. Okay? A bit of a philosophical perspective, maybe. Sorry. And then this way of interpreting the model will be translated in the LPy through the function animate. If you click animate, what is going to occur? Your model string production rules will be applied to the axiom, and each time a new derivation is made, the geometric interpretation will be computed. So at each step, the geometric interpretation will be computed, which means that it will be possible for the turtle to draw on the screen all the geometric interpretation at every step. It is different from what occurs in the run, because in the run, you compute with the rewind, you compute the initial state and the geometric interpretation of the geometrical state. And then the run goes through all the derivations without computing any of the geometric interpretation in between, and just give the geometric interpretation of the result. Okay. This is nice, except when to compute here the model, you need to have the result of the geometric interpretation. Okay, because the geometric interpretation may position the different organs in space. Imagine that light is coming to the organ. I need to know where is the organ, the x, y, z coordinate of the organ. Okay? But if I use the run and I compute everything without computing the geometric interpretation of the object, I don't know where are the leaves. Here. So I would need a means in order to transform a bit this, so that I can get the geometric interpretation when it is necessary. But it's a bit already advanced programming. But you can see here that this is nice in Jean, but it can induce a number of difficulties that would need to be solved. Is that clear? Yeah. Any question? You may try now this example that I wrote, well, not too complicated, but a bit already advanced, where you have two production rules and a couple of interpretation rules to see how this separation can be actually handled during a program. So what I propose is that you try this example and try to understand what it makes.
Can you remind the difference between produce and end produce?
Yes, when I have only, because, okay. I can have an apex that it depends on the certain variable, say the age or the progress in the derivations. And I want to express a production rule about this apex. So I will, but this apex will produce something depending on the value of n. Okay, so I can write something like this. If n equals 10, produce a long internode. Sorry. A short internode me see, because I need to construct so that it works. Produce a lateral leaf. And here, instead of putting equal 10, I will put greater than 10. Okay. Produce a leaf, and else produce an internode of size 10 millimeters. Okay? If I write this in this way, I will produce, as long as n is lower than 10, I will produce small internodes. Okay? So when I get to, to the position of 10, this rule will apply and not this rule. And then I will produce a leaf, which is lateral. So let's say that here I will have a leaf. Okay? Now imagine that I want to continue the axis and produce, I continue to produce internode. Then I just say I need to produce lateral leaves and remove this else. And the produce will be here. Okay? So now it means that I'm going to do this. And each time I will have a leaf, because this statement will apply. Okay. Except that if I keep the produce here, I will not have this. I will have this. I will have the 10 internodes. When I arrive at this produce, I will produce this. And as the produce quits the rule, makes the system quit the rule, I will never go to this point. So therefore, here I will have nothing. So if I want to allow the system to continue, I need to put an end produce saying that produce, but keep going with the same within the same rule. Okay, so here you could imagine that this is return statement, whereas if I put end produce, I say produce the leaf, but do not return from this rule. Is that clear?
But why would the produce L be a return statement and not the produce I?
Yes, because here, when you get to this point, you want to return. You have nothing to do after that. So I can put the produce here. But if you put end produce, it won't change. So so this to say that actually you just need to put end produce everywhere, and this will work perfectly.
Okay.
Okay? But actually, as both things exist, when you read the program and you see the difference between the two, you need to know what it means. Okay? Is that clear enough? It's important. Well, I think by practicing it, you will understand better how it works. So here you could replace all the produce by end produce, and it works. It will work. So here, and end produce, you see here as well. I use end produce because I want to compose another way to present this, very briefly. This is genial. Another way to present this is when I have a long produce, so something that will produce a very long string. So A, B, C, D, E, F. Look, here I am producing things that start to be a bit long. Okay, with parentheses maybe here, with brackets. So I can just split this. Instead of making one statement, I will use end produce. AB. Then I end produce, I continue the production. going to the next line, saying I produce the CD, and then I produce also the rest of EF. So this is equivalent to this. Okay? To be equivalent exactly should be produced in the end, but so final step for you when you are writing something, I mean, just use always the end produce, and it should be no harm. Okay. So would you? Okay. So here, there is an apex. The apex gives an internode and another apex. So it's typically the same rules that we are using since the beginning. What is added is the fact that the internode that is produced can evolve in time. So you have this evolution here. And then we will see how to interpret this. And then, so you see here, there is nothing that is related to the geometry that tells the turtle how to work in here. I have geometrical parameters. For instance, let me see. Yes, the alpha is the phylotactic angle here. So I have geometric parameters. The L is the length. The R is the radius. So the parameters, the geometry parameters, they're part of the model. Okay, I want to manipulate the sphere. So the radius of the sphere is a model parameter, is part of the deep aspect of the model parameter. But it's not the sphere itself, it's the radius, it's the parameter of the sphere. And here when I go to this place, I say how to use the radius. I give a meaning actually to the radius. Because here, if I don't tell you that this is the radius of a sphere that I have in mind, you don't know what it means. Here, you will know what it means at this point, because the the n, which is okay, so the radius that is the parameter r in the I module will be interpreted as the thickness of the cylinder. So now I say what is r in the interpretation rules. Okay? You can try to play with this. Couple of minutes. So, if you were to explain this to other people, would you be able? Or it's super complicated for the moment? Nabil?
Maybe in gross ideas, but not in detail. I think I would be easily caught in a trap if.
Yes, for the moment it's clear. Yeah. It's clear. But I can rephrase what you are looking at in a way that you because you need to understand the connection between this, and this is difficult. I know that it's difficult. Okay. So these are a number of parameters for the model. Constant values or initial values, these type of things. I have the axiom. Axiom is an A which I have in mind. This will be my apex, the plant apex. And I need to say this to you because it's not written in the text. But when I designed this, I had this in mind since the beginning. So an ape, and now I want to say that it will be representing a growing plant, and I want to say that this apex will grow. So I need to use a production rule, and the production rule says basically that an apex will be transformed into an apex. Now you see that this transformation goes with the increment of n, and the n started with the value 1. So it means that each time I will apply the derivation, n will augment by 1 unit. And this would correspond, for instance, to the age, to a certain notion of age of the apex. So each time I apply a rule, the apex gets 1 time unit older. Now, at the same time that I'm producing this apex, just before, which means below, in my mind, it produces as well, so this apex produces this and this, so it produces as well what is called I, which in my mind is an internode. No, an internode, obviously, will have always the same number of parameters and always in the same order. And here you can see the order and the names that I gave to these parameters. And the names are L, R, and A. L is for length, R is for radius. I could use whatever name, huh? But in my head, it's L for length, R for radius, A for edge. And A for edge, you see that, oh no, sorry, A is not for edge, it's for phyllotaxis. It's a phyllotaxis angle, sorry. So here, so I could put more precisely phyllotaxic angle in full ASCII form here, but it will be clearer. I know that is the phyllotaxic angle because here I look at what was given when the I was created, and what the value that was given is n, which is the h, times the phyllotaxic angle, which is the angle between two consecutive leaves. Okay, so if this angle is 120 degrees, when n is equals 0 or equal 1, it will be 120, the value here. When n equal 2, it will be 240, and so on. So in the beginning here, I need to initialize the values when I create the internode. Here, this is important to understand this. When I put a rule, I do not assume that the parameters are specific values, because I say an internode of length L, of radius R, of phyllotaxis A should become this. And here I don't have specific values for L, R, and A. So this is why the rule is using variables. It's like a function. Okay? The rule, you can see it as a function. So function of L, R, and A is a certain algorithm of L, R, and A. Okay? So it's really a function. You could really read this as a function. So you have the variable of the function. Here you see that I don't have the variable. I have values. And it's very important to make the difference between the two. And why I have values here? Because it's not a function. Because it's not on the left-hand side. It's not a function. Because here, I say what I want to create in the beginning. So what I want to create an I at the very first step, which is 0.1 long, which is 0 of radius, and which has a certain phyllotaxic angle. And when the system will interpret, so the first time, I will write for you the first derivation step. This that I'm currently explaining, you should have it in mind after that all the time. And you should come back to this, always. So if I take the A of 1 and I apply the first derivation rule, the first derivation with my production rules. So the A becomes what? There is only the first line that applies, which is I of 0.1. No, sorry, 0.1, 0. Let's say alpha, this is the angle, and A of 2. Okay? Here I applied the rule A of n. No, so this is step 1. This is my new L string. I need to go to the next L string to see how the system will continue. And I will apply, for the step 2, I will apply a second time all the rules. But here, you see that I need the first rule. So from here, I need the I rule, I of L, R, and A. and I need here the rule A of n. Okay, and for the rule of I, you see what is going to happen to I is going to increment the length and increment the radius, which means that I want to make it grow with time. So, and the increments, they are given here. They are constant values. And my increment here is 0.1, which means that I will have 0.2. The other one is 0.01. And then alpha doesn't change. And then the A of n becomes A of n plus 1, and this is A of 3. So you see how it... Oh, sorry, I forgot the I, because there is an I here, which is the same actually as this one, so it becomes the same value. It's not the same internode. And now the A of 3. Okay, so you see what is happening. A is becoming older and older and older. And the i's, I have more and more i's in my L string. So 0, 1 I, 2 i's, 3 i's, etc.
But these two steps are part of derivation 1?
These are part of derivation 2.
Why?
So this is derivation, let's say, this is derivation number 1, and this is derivation number 2.
And I didn't understand one thing.
Why you didn't apply the second rule, I, L, R, I, in the derivation 1?
Because there is no, here, there is no I.
Okay.
So the result of the first operation doesn't apply to, we cannot apply the rule if in the result of the first operation.
This will be the second step.
Okay.
It's really, I mean, I know that is difficult, but actually, if you think, it's extremely syntactic. Okay? I take a L string, and you need to go to this simplicity, because by thinking in terms of procedural things, procedural way of thinking, it's more complex because we are used to a certain control of the different the loops and the while statements, etc. Here there are no, basically. The system is doing the loops for you, and you are just keep in the frame that I gave you. L system is a rewriting system. So it basically goes from one string, it basically acts on strings and gets the strings, apply the rules in a sequence, and get the result. That's it. That's it. It's the recipe. And if you keep to the recipe, you will make a very good cake. Was that clear enough? Yes? So I take time on this example because after that it's a bit always a variation on that theme. So if you get this very nicely, you will follow well.
Just another last question.
Go ahead, this is the point.
And
For example, A-N, we can think in this part that A is like function where we can replace the n by the index of the step.
Yes, exactly. I just make this point even more clear, I mean, so that everybody follows. When I write a rule like this, A of n becomes I of 0, A of n plus 1, let's say. Okay? It's exactly as if I would write f of n, A being the f, equal, let's say, n plus 1. So this is mathematical definition. This is L system definition. But it's what I say is that this is exactly the same way of thinking. Here, this is a free variable. I can give it any value, and it will make it possible for me then to compute the result of applying this f to this any value. Okay? So this is the definition. So this is a definition. If I want not to use the function, I need to take a special value for the free parameter. And then I will be able to compute an instance of the result of this application to f to something, which is before. Here, it's exactly the same. You define the function by here in the production rules, okay? But you apply when the function will be applied, actually the L-pi will apply it for you on the L string. So when I'm doing this, I am computing this. I apply, you see here this is the function. I apply the function to this value of 1, and then I get the result.
Function of the derivation step.
Yes, the
Parameter.
derivations are applications of the production, which has the function, to specific values. And then I get values. L string is basically a value, and production rules are basically functions, and you apply production rules to values to get new values. Is that clear? And the parallelism is very exact. So you can really keep this in mind as a sort of model of how to think about the thing. Okay, and thank you for asking the question, because I know that, it's difficult. You don't, it's not obvious, this. But you need really to have this type of model in mind in order to interpret correctly what is going to occur. So it's important that that is very, very clear. Is there any other doubt of how to interpret all this? No? Good. Okay, so last point in this part that...
I'm sorry, but I thought the example was to illustrate how much the production and interpretation can be, and well, maybe it was obvious, but you didn't.
Ah, yes, sorry, I didn't finish the explanation. All right, because I was going on this. Yes, so here, what you see is that I'm going to compute things that have no meaning for the turtle. Okay? So I am instantiating values all the time. So this is my model, the model of what is a growing plant. And now I want to take this model and to interpret the values in terms of geometry. So these are the geometric interpretation. And here I say, okay, if in my L string, for instance, this one, if I have an A, how should I plot it on screen, or how should I create the geometric model of this part? It is defined by this rule of interpretation, which says how to interpret an L, and how it is by plotting a sphere which has a certain size depending on the edge. So meaning that the size of the sphere progressively with time will increase, because it is an increasing function of it. And similarly for I, how should I interpret this? It's not very clear. How should I interpret this? Well, here I say, and here it is really the very place where I will say L is the size of the internode, because I say L is a parameter of F, and the first parameter of F is the length of the cylinder corresponding to the F. And the second parameter is the radius of the cylinder. So by saying this, I'm saying, please interpret the I, well, not please, interpret the I with a cylinder of size, of length L and radius R. It's good for you?
Just to make sure I understand end produce here in the internode end produce, it means that we continue to we continue to increment the internodes, and also
Yes. Actually, here I did, okay, I was commenting as if the end produce line didn't exist. This may be your point, and I'm sorry because I forgot to mention. So no, we comment. So imagine that this line doesn't exist. You would have a straight axis. Okay, but actually you don't have a straight axis. You have an axis that looks like a fishbone geometry. And actually, this is due to this, because here I put between brackets, I put an F. So the idea that I had behind was that this would be something like a leaf. I didn't consider to really put a leaf here, but this could be a leaf. Actually, you could try to put a semicolon just within the first, after the first opening bracket, semicolon, and the color of a leaf. And you will have cylindrical leaves, at least from the color you can guess.
And why did you use twice R in the produce of the in the production rule for the internal? Like
Yes, because this statement says that it's a bit of subtlety. This statement says that you take the turtle as a state with a width, with a position, etc., but with a width. So the turtle at some point, let's say x, y, z, has also a width that is being computed, and at this point there is a width, certain width. So let's say that the width is this. If I write f x l, no sorry, f l radius, and so I will go upward by l. If the radius is this statement blends the new radius with the old width of the turtle. So you would have, in places, in particular at the beginning, you would have this type of phenomenon. So in order to avoid this, I say first, change the state of the radius of the turtle, and then draw your and this will make this. Instead of this, it will go to the final radius, and then you could draw your cylinder in this way. Okay? Other questions about this example? You need to understand fully this example. Well, one way to understand nature or computer science is to shake the stuff. So if you want really to understand, you would need to change everything here, make your own investigation of how this behaves when you modify the different rules and things like this. So I encourage you to do this, to check whether the model that you are constructing of how all this works is robust. Yes?
And maybe you said it yesterday, but all the terms for encoding a geometric shape. So you have a list or a list of.
Yes. And this is given. So, for instance, we saw this cylinder, we saw the sphere, and we saw others during the.
what is the slash?
Slash is to change the angle orientation, a particular angle, and we will come back to this. So it's like plus and minus, but in other direction of space. Other questions? Okay. So I encourage you really to play nicely with it. Did you make animate? Did you push animate on this? And you see that it starts to mimic a bit a continuous development, because I used the increment of length when I increased the size of the internode. And what you see is that it's exactly what occurs is exactly what I say here. When I use animate, at each step there is a small increment that is computed of the length of the internode, and then I display it. So it's like a movie where you plot consecutive images of a very slowly changing object. And the result is that you have the impression of this movie. Okay? And the last example to finish this, this part of the session is this one. How to create axioms. So you could go to the, so in axioms you could write, because for the moment we just wrote L strings in the axioms, which is a bit boring. I mean, it's a bit tedious to enter. If you want to enter a full plant or hundreds of plants in the scene, it would be a bit difficult to put it by hand. So instead, what you can test is that instead of putting just a L string, you could use the axiom as a production rule itself. And in this case, the production rule will be interpreted at the very first, before the first step, and will create your scene. So this very powerful way of creating your initial state of the data. So would you like to try? It's in example 9, and you can simply try the example and check how it is easy to construct, for instance, a scene with many plants. Okay, so you see in example 9, you see that I didn't create the whole plant, because this, you see the production here that I use only produces a cylinder. Okay, but if I make it more complex, I could create a full plant. Okay, so it was just to show you how by using the axiom as a sort of more complex object, I could create a matrix of plants on which I could plot all the different elements of the different seeds, let's say, and that will grow afterwards independently of each other. So it is as if I had defined, maybe I should augment the size of the text. It is as if I had defined an axiom with many A's between brackets, separated by a small interval that is represented by the F's here. The F in X and F, the delta in X and the delta in Y. Question on this? You feel confident about this?
So small f is moving without plotting.
Exactly. It's like big capital F without creating the cylinder. But you move the turtle.
Only way I am fighting against myself, because when I see the minus, for me it's math.
Yeah. So you need, you need to forget a bit things to better come back to them later on. Don't worry. Here, everything is module. There is no mathematical interpretation. Everything is module.
It's not conscious.
Yeah. I know that it's difficult in the beginning. I had the same difficulty, actually. Other questions about this? And you see the use of the end produce. It couldn't be done without the end produce here. You see that is extremely useful, because each time that I would encounter a produce, I will quit the rule without the possibility to increment the axiom. Okay?
But here you're kind of mixing geometric interpretation.
Yes. So what I was saying, it's like really, I said yesterday, it's like computer design patterns. It's better to use them. You may be super strict in using them, but you may be a bit more loose in using them. The better, the more strict you are, the better will be your code, because this is the point of a design pattern. what occurs is that in many times I am not so sharp in the separation between the geometry and because it's not useful. But in the places where it is useful, I'm very strict. So you need to know where are the places where you need to be strict and where are the places. So it comes with the expertise of the code. Because the point is that if you use the design pattern up to the end, it's a bit also heavy. So in order to avoid heaviness, you need to make compromises, and this is where the expertise comes. But you're right. I mixed the two elements. I could have made a very much simpler code where I put just let's say seeds. I could say seeds. I put seeds at position x, y, or at one after the other, and then in the interpretation rule, I would give the fact that this seed should be interpreted as an F followed by an A, but so followed by a cylinder.
I have a question about the design. For example, in the interpretation part, semicolon means something geometrical. F's. As we can separate the geometry from the conceptual things, why didn't you use simple, more intuitive terms? For example,
It's not.
It's not.
It actually it was introduced. There in everything there is a bit of history, and initially I don't know exactly whether it is Przemek Przemkiewicz that chose these different symbols to represent the different actions of the turtle. But what is true is that in any case, all these symbols are defined in the original book that I presented, which is the Algorithmic Beauty of Plant. And they are given a meaning. And then for backward compatibility, we still use this. Actually, I think if you go in the help card, there is a sort of translation of each in more standard terms.
Okay, so we can, for example, comment this in.
But you know, it's like people that are using Emacs. I was a user of Emacs for a long time. I didn't type in the command. I had all the keyboard shortcut, and I knew the keyboard shortcut. I no longer do it, but I knew the keyboard shortcut. And then when you knew them, it's super rapid. So instead of putting set color here, I just put a semicolon, and that's it. But in another way, it's less readable by other people. So it's good design pattern to put the full name of the command. Okay, and the last point, still in the context of how to use the axiom. Well, you can have your L string coming from the outside, and you could plot, like for instance, someone is giving you a plant that was mapped from the field. They use the L string notation. How do you get this in the plant as an initial state for the plant? You can go in example 9 point, I don't remember, 9b and 9c, and where I plotted a rice I used a rice panicle that was acquired by my colleague Yves Caraglio a long time ago. Okay, and what is super interesting here? So this is the rice panicle. The rice panicle doesn't come with a geometry. It was measured in the field, but only the topology. So if you go to the S string, you have I think no instruction about geometry. And look, so I'm reading here by this. I just open the file, read the file, get the string from the file, and then I use the ns produce. So it's the new command. It's the ns produce. No, this one. Can you take this away from me so that I am not tempted? NS produce that takes a L string as an argument. And if you write L string of the string that you have read, of your file name, it's a string, stg, then this will produce a L string corresponding to the L strings stored in the Python string. Okay? So it's a way to take a Python string, chaîne de caractères, string of characters, and to use it as the right-hand side of a production rule. Clear? So it's a special statement to do this type of thing. Okay, so this is what is done here. And look here. We don't go into the details. You can try it. There was only topology in the L string. There was no way for the turtle to interpret. So I used interpretation rules. Okay, it should be. I used production rules here, but I could have used interpretation term. It would have been better here. Actually, to give a meaning, a geometrical meaning, to the topology of the plant that I was reading. And then here I define everything. I define on which side the axis should be found depending on the rank on the axis. I define what do I define? Interpretation is below. Interpretation is here. So I take. Okay, I restart because this was a bit confusing. I use production rule to transform the symbols that are V, E, and S that are actually in the file to give them a meaning corresponding to a branching segment. It's a sort of translation from the language that was used to describe the string in the file to the language that I want to have in LPy. Okay, so this is translation. And then I use this, I interpret this translation by putting a color, putting an angle between the different segments, and that produces the final string that I see. Okay, so you just need to understand in the principle. So what is extremely important, you can get, for instance, trees that come in any format. Usually any format will be a format with parentheses, because a tree needs to be bracketed if this is in a computer. So you will get this. You can read this, and because L system is a rewriting system, you can rewrite anything in anything. So you can rewrite the stuff in a way that your turtle will be able to interpret the string. And how you do this? By just giving the right production rules and the right interpretation rules to give meaning to the correct symbols. And it's quite, you see, it's really extremely short program. Huh? It's 15 lines or something, or 20 lines of code. Okay? And you have another example, which is a walnut tree. So it's so this one I like it very much because this was my friend and colleague Hervé Sinoquet, passed away, unfortunately, more than 10 years ago. And in his memory, let's say, this is the first tree that Hervé digitized. So it was the first tree ever digitized. Okay. It is like 5 or 6 meter high. So it was really a challenge at that time. It was in the 90s. And we used the code that I designed specially, like using MTGs and things like this, in order to capture the different information in the tree, the topology, the geometry, etc. And here we had the coordinates, the 3D coordinates, because there was a digitized device that makes it possible to get the 3D coordinates. So Same, I have the file. I can with topology and coordinates and length, coordinates and diameter and things like this. And then I use, you see production rules here, but it could be interpretation rules. It would be better to be interpretation rules. I use it to plot, to interpret the data, because x, y, z is the point in space, but doesn't say where are the branches. So you need to reinterpret the cloud of points with the topology in terms of a geometric representation. And you see, it's quite short. Okay? Questions? I like this tree. It's a walnut tree, by the way. Well, it's written on the file, but it's a walnut tree. And for instance, what you could do, well, you could try to do it if you like. You could add leaves on this, because now you know. I would just need to explain to you what is the S, what is the U, and what is the V. What do they represent? Actually, the U and the V are the shoots, so the new element of the year. So if you want to put leaves, you would put leaves on the U and on the V. And then you could reconstruct the crown of a tree that is a leafy crown, without having really measured the leaves in the real plant.
So I would think it should be a great compression for walnut tree data to have it as an string. Yes,
actually, it is true. Usually what people do nowadays is that they take a point cloud using a laser scanner, for instance, and you get a huge amount of points, and what is difficult is to interpret them. But at that time, it was like 25 years ago, something like this. It was the first tree ever measured in this way. And actually, Hervé, he bought a magnetic sphere that was emitting a magnetic field in all the space. And then there was the tree here, super big. It's not the scale, because the sphere would have been a bit like this. So you had the big walnut tree here, like this. And then what he did, it was possible from the sphere to have a mouse, a small mouse, that was able to sense the field emitted in the 3D space. And with the mouse, you could click on a point and get the x, y, z coordinates because of the field that is vanishing away. You have the gradient of the field, and then you can recompute everything, the x, y, z, and the orientation. Let's say theta, phi, and psi. So you get this information for each point that you click. So it was just in 3 dimensions. You know, you imagine this. It's not like clicking on a sheet of paper. It's like clicking in 3 dimensions. He was clicking at different positions of the plant, all the segments, like this, and get the 3D coordinates for segments that are sufficiently big enough. So already this was a way to compress, just by the measurement, to compress the tree. Because the idea was then to interpolate between the different points. He was measuring the diameter also at each level. He was measuring a number of other attributes, and then created this file. And then putting all this information within the L string makes it possible to reconstruct the plant in this way with a strategy that we designed at that time. But this was fun. I could show you the device that we used.
He was climbing in the tree.
Climbing. Actually, he was not climbing in the tree. Was partly climbing on the tree, but he built a huge scaffold in wood because there is a magnetic field, so it cannot be metal. You could climb here, and then and this was during 1 month or even 1 month and a half or something like this, just to measure all the tree. This was really a real challenge.
How many points Leslie?
I don't remember thousands, but I don't remember how many. I didn't use the... Because we used the tree after that to do a lot of publications, you know, a lot of work to interpret. Because after you can add the leaves, you can see how this interact with the light. You can grow the... You can remove... This is something that we did. You can remove part of this, put apices, and then grow the apices with certain rules that you have in mind, and check whether you get close or not to the previous, to what the tree was looking like. Well, you know, this type of thing. Once you have this type of structure in the computer, which is a real data, it has a great value because it's real data. Then you can do extremely a great number of things related to scientific studies. Other questions? Okay? Okay, so we can have this pause now.